In this video, we are going to go through some of the introduction for Lesson 21, the Fundamental Theorem of Calculus, and do example 1. So in the lesson before, we were looking at definite integrals and how those could be used to find areas under curves. And a particular application we looked at is when we looked at the area under the velocity curve that gave us our distance traveled, that net change in position. And unfortunately, we haven't been able to evaluate complicated definite integrals yet. That is, we haven't been able to exactly say what a signed area under a curve is. We've been able to estimate them using Riemann sums. And if I gave you an example where secretly you didn't need calculus, like we were finding the area of a half circle, we could just use geometry. The fundamental theorem of calculus is going to give us a very, very, very slick way to evaluate these definite integrals. There are two parts to the fundamental theorem of calculus. The first part says that for continuous functions, differentiation and integration are inverse operations. They do and they undo each other. In other words, integration is anti-differentiation. The fundamental theorem of calculus part 2 gets at evaluating definite integrals in a very, very, very smart way. Instead of looking at this, or instead of evaluating it from the definition as a limit of a Riemann sum, in other words, adding up areas of rectangles and taking the limit as the number of rectangles goes to infinity, we're going to evaluate this limit in a very slick way by asking a completely different question. It'll be beautiful. All right, so our learning objectives are to understand the outline of the proof of the fundamental theorem of calculus part 1. We're going to visualize how differentiation and integration are inverse processes, as well as get some visual intuition for fundamental theorem of calculus part 2, and most importantly, learn how to use the fundamental theorem of calculus part 1 and big time part 2. All right, so let's go ahead and do example 1. I'm going to introduce a function to you. You can think of it as the area so far function. So the graph of f is given here, f of t. And then a of x, it's a function of x, right? X is up here in that limit of integration. It is calculating the area under the curve f as x goes from 0 to wherever we want to stop it. All right, so first find a of 1. This is finding the area under f as x goes from 0 to 1. That's still pretty new to us, so I think I want to write that sentence. And it is a signed area, meaning positive or negative. And we can say as x goes from 0 to 1, but how about I say bound by the vertical lines x is 0 and x is 1. Right? That's where it's telling us to stop integrating. So from 0 to 1, we're looking at finding this area of that quarter circle. All right. So what is the radius of that circle? The radius of that circle is 1. The area, it's a quarter of a circle, so a quarter pi r squared. The radius is 1. We get a quarter pi, or pi over 4. All right. Remember from lesson 19, the definite integral is another way of asking to find the area, that's this area right here, pi over 4 units squared. Find the area under this curve bounded by these vertical lines. X is 0, x is 1. The next one, now we're finding a of 2. I'm just using function notation right here. Notice that the limit of integration is now stopping at 2. In fact, I want to use a different color. Right? Stopping right here. So what this is asking us to find the signed area under F bound by, we're still starting at 0 and stopping at x equals 2. All right? And so that is the blue area that we already found plus this green area. Which is just the area of this half circle. One half, because it's half a circle, pi radius squared. Again, the radius here is 1. Radius is 1. So this is equal to half of pi, or pi over 2. Lastly, we're going to find a of 3. All right, so there's where I'm stopping. This is finding the signed area under the curve f, but bound by the vertical lines x is 0 and x is 2. Sorry for saying x is 2. I was just getting ready to copy the text above, and so I read a 2, right? We are integrating as x goes from 0 to 3. So that area is the area we've found thus far, right? Here was a quarter pi, then we went 2/4 pi, i.e. half pi, and then now the area below the x-axis is negative, right? Though that's what we mean by a signed area. If you were estimating this with Riemann sums, the heights, the y values of all of your rectangles would be negative. So just copied that drawing right here. What is this area? This is that quarter pi plus another quarter pi, and then minus whatever the heck this is. Right? What is this? That's the area of a triangle. The base is 1. The height is 1. 1/2 base times height. That's 1/2. 1 times 1. The area of this triangle is negative because we're below the x-axis. 1/2 base times height, which is just minus 1/2. All right? And I did in question 2, when we did a of 2, I wrote that pi over 4 plus pi over 4 as 2 pi over 4, or pi halves. Then minus 1/2, and that looks beautiful. Common denominator, how about pi minus 1 all over 2? All right. So these are your 3 answers. 2 things. One, this is fairly new for us to think about the definite integral as an area. We were doing that in the previous lesson. And then secondly, this, now I'm looking at a function. A is measuring out the area under the curve f, and then at a given input, stopping at a particular x value, it'll tell you what that signed area is thus far. And I had us stop at real convenient numbers, right? We found the area under the curve from 0 to 1, that's the blue. Then we found the area under the curve from 0 to 2, that's the blue plus the green, which I wrote as a purple. And then a of 3, we're finding the area under the curve as x goes from 0 all the way up to 3. We were subtracting the area of that triangle because we are below the x-axis, that signed area is negative. This area so far function is something that we're going to be looking at in the next video on the Fundamental Theorem of Calculus Part 1.